Thanks for coming today, everyone. So, like I said, my name's Liam. I'm in the third year of my PhD, and there's some work I did earlier on coordinating networks of renewable energy resources, which is basically what I'm going to be talking about today. And the rest of the title is how we are going to be modeling and solving these problems through some game theory and getting into some optimization techniques. It's going to be light on the technical details, but I'm happy to answer questions later about the nitty-gritty parts of this. So let's get started. So I think how most of us, or how I think of power plants, and I think how most cities are run on power plants is you have one big building somewhere far away from the city that is generating power through like oil, coal, gas, maybe something a little bit fancy like wind farms. But if we think about fossil fuels, these are like traditional power plants. They generate all the power, they transmit it to the city where people are going to consume this power. And this is a very consistent method of power generation, right? If we need more power, we burn more, whatever fossil fuel. If the demand goes down, then we can just take our generation down a little bit. So there's no major natural fluctuations in this generation. Obviously, stuff goes wrong in power plants, but there's no natural fluctuations. It's very consistent and it's pretty adaptable. So what we would like to move towards, maybe on some kind of vague societal level, or at least me personally, is move towards renewable energies. And so what the setting we're going to be looking at here is we've got some neighborhood, some small-ish region, maybe on the level of a neighborhood or a town or a city. And we want to try and fill their energy needs with renewable energy sources. These are solar, wind, geothermal, biomass, stuff like that. And so we are looking at a network of these renewable energy resources, and somehow we want to generate all the power we need. We might need quite a few more sources to do that than one big traditional power plant. And the problem we are looking at is what is called a virtual power plant. So if we have a lot of smaller renewable energy sources, individually there might not be enough to meet all our power needs, but in an aggregate, we might be generating enough power to fill the role of a traditional power plant. So a virtual power plant in that it's spread across a lot of different locations, a lot of different sources, but it's filling the same power plant role in ideally. And so this idea isn't super new. Depending on how you look at it. So it was proposed in the late 1990s. It was pretty theoretical. It was very theoretical when it was proposed. We didn't have the kind of technological regulation groundwork for this to be super feasible when it was proposed. But in the last 30 or so years, renewables have become a lot cheaper and a lot more efficient and accessible through technological advancement, and then also some relaxation of regulations and government incentives to get into renewable energy. And also it's real. So it is actually, these kind of networks are happening now. So there's one big one in Australia, in Adelaide. It's about 8,000 households that are serviced, that have access to this virtual power plant, and they can get their energy needs from that. And there's a few in Europe and a few big ones in the US. And one that I wanted to highlight, there's a town in Germany called Feldheim, which has a completely independent power grid. So they are not dependent on the national power grid or on big power corporations. They produce all their power themselves with various renewable energy resources. And so they are kind of self-sufficient. They're kind of independent from traditional power plant things. So these things are real. There's not many of them, but there's a few kind of case studies we can look at so that this does actually work. It has a few advantages, and it is a nice way of making renewable energy a bit more scalable. So to kind of drill down on why virtual power plant might be a nice idea to try and implement. So we can smooth out the generation of power from renewable energy. So like I said, traditional power plants, they don't have big natural fluctuations in the generation of power. Something like solar panels, you get no power at night. maybe less power when it's cloudy. So there's kind of natural fluctuations in that. If we can aggregate some renewable energy sources, if we include batteries, then we can start storing power and using it at night or when we have less power. We can try and smooth out the generation and try and meet the demand better. And also, speaking of the demand, so if I have a solar panel just for myself, I'm just using it for my things, maybe I'm generating more power than I need to use. I can try and store some of the excess, but otherwise I'm just gonna not use the rest that is generated. But if my neighbor also needs some energy, then, well, if I'm just using my solar panel for myself, then they're out of luck. But if we are in, well, I mean, not out of luck, I have access to the rest of the power grid, but in this renewable energy world, they don't have any alternatives. In something like a virtual power plant, then the excess power I generate can go towards them and their needs. So we can, it's a bit more adaptable to demand than isolated renewable energy sources. And also, like I said, so with this example of Feldheim in Germany, we have a lot of different renewable energy sources that we can kind of strap together. So solar, wind, geothermal, biomass. It doesn't need to be all generating the same thing. Like a traditional power plant might just be a coal power plant. And also, in something like a coal power plant, it's far away from the city for like pollution or noise or smell reasons. And you need to transmit the power to the city where it's actually being used. And so there is a loss as we transmit it along power cables. If we are generating power from something like solar panels, there's a few on buildings around here. So they're within the city that is using the power. We can get a smaller transmission loss. But obviously, this is not a perfect concept. There are quite a few challenges. And from our point of view on the mathematical side of things, number one is coordination. So we have different generation resources located in different places. It's not all concentrated in one building. So now we need to, make these things work together. Potentially, And second thing is not only are they in different locations, they're potentially owned by different agents. And these agents, they're humans. They might be selfish or driven by profit motive, or just by personal interest. So we have to manage conflicting priorities as well, which is going to make things a little challenging. So just to give you an illustration of what this is going to look like in practice, what are people doing in a virtual power plant, or at least what's the problem we are looking at? So we have a group of agents in our virtual power plant, let's say 5 of them here. And the idea is they can generate power, they can buy power from the grid or from the energy market, and they can sell power. And so in our time horizon, our agents are going to decide how much am I going to charge, how much am I going to discharge in each of my time periods. So for this agent up the top, in the first time period, we're choosing to charge by 4 kilowatt hours, so either buying it or producing it. In the second time period, we're not going to do anything. We're just going to sit on it, we're fine. And then in the third time period, so minus 1.2 kilowatt hours, we are discharging power, or we are selling it. And so with a schedule like this, over however many time periods, we can associate a cost to each of these actions, or like a profit to selling electricity. And so we can associate a cost to a full schedule. Right. So in this kind of toy example, we have a cost of $44.60. This might be over a few weeks or maybe a month. And so everyone else in the virtual power plant, every other agent is making these same decisions. How much am I going to charge? How much am I going to discharge? So this is the problem we are trying to model, and ultimately we want to try and manage this towards a good solution. So just to write down a few of the details. So our problem, we have, like I said, some time horizon that's broken up into discrete chunks. This might be hours, maybe days, maybe minutes, depending on what your resolution is. And we have some kind of population of agents. We're going to say they have power banks, but basically they have the capability to buy power, produce power, store it, and sell it. So breaking it up into charging and discharging. And each agent wants to decide on a schedule for themselves over this horizon. And this schedule is going to be broken up into each of these time periods, and they want to figure out when do I want to charge and discharge my power bank, and how much do I want to charge and discharge it. And so we are assuming that agents are motivated by personal cost. They are rational, and then also, I think, maybe selfish as our modeling agents. And this cost, we break it down into the price of power for this schedule. So this is the cost of purchasing it and the profit we get from selling it, but also some kind of penalty for, if I would like, if it's convenient for me to charge overnight, and my schedule tells me to charge, actually, we want you to charge it at 8 a.m. That's inconvenient for me. I don't like it. I'm going to put a penalty to it. So we want to get the smallest price and also a schedule that kind of meets our personal preferences. Okay. So in all models, we have our assumptions. So we're assuming that agents know what the price of power is, or at least have some reasonable forecast of it, and that they are selling their excess power directly to the grid. So we're not choosing who to sell it to. We say, I choose to sell it, and it's going into the grid. Other people can buy it if they want. And also, this power grid supports other users. They're not engaging in the virtual power plant, so they're not choosing to buy and sell, but this is going to inform what the demand for electricity is, how much can the power grid support. So this is one part of this power ecosystem. All right, this is the problem we are looking at. So what are we doing here? What is this presentation about? So first of all, we want to model what this problem is. So what is the virtual power plant schedule problem? And then not only do we need to have a problem, we want to find solutions to this problem. So the first part, we're going to describe what the problem is, and the second part, we're going to propose a method for solving this problem that is, has some advantages over existing methods. Okay, so our overall goal is we want to find an optimal set of schedules. So a schedule for each agent that is in some way optimal. And so the obvious next question, at least for maths people, is what exactly does this mean? It's nice to just say we want it to be optimal, but what do we mean by that? So we are considering a set of schedules is optimal if each agent can't get a better outcome by individually changing their schedule, so without cooperating with other agents. And so this has a special name that has been pretty well studied as a Nash equilibrium, or actually a generalized Nash equilibrium, but there's the distinction is kind of technical. So it's a Nash equilibrium. I'll be getting into what that is in a second. So our model for the virtual power plant scheduling problem, this is called a non-cooperative game. So it's a mathematical game where agents aren't allowed to cooperate with each other, and they aren't allowed to team up and decide what a good solution is. Because you think, real corporations sometimes don't team up and find out the best solution. And like I said, our optimal schedules that we are trying to find are Nash equilibria, or generalized Nash equilibria. Okay, so what exactly, so there's a few technical terms up there. What's a non-cooperative game? What's a Nash equilibrium? So as a simple example, not related to renewable energies. So a non-cooperative game, there's a nice example, it's called the stag hunt. So we have two agents in our network on the left and on the top, and they want to find they're in some kind of hunter-gatherer society, they want to find some food for their family, and we're going to do it by finding an animal to kill and harvest. And so we have two choices. You can choose to hunt the stag. Stag, big, lots of meat, lots of food for lots of people, but it is riskier to hunt. And the second choice is you can go hunt a rabbit, which is much smaller, much less meat, but much less riskier. Rabbit is not going to harm you that much. So your objective, each agent's objective is to maximize their personal harvest. We don't really care about the outcome for the other agent. And they have some constraints on what they can do. The constraints here are just, do you hunt the stag or do you hunt the hare? Simplish constraints. So this is our example of a non-cooperative game. What is a Nash equilibrium in this example? So there are two Nash. There can be more than one. In this case, there are two, which is we both hunt the stag or we both hunt the rabbit. So what exactly does that mean? If we There's going to be a bit of delay on this, isn't there? No, there it is. So if we go back to what I said before, a Nash equilibrium, agents can't get a better outcome by individually changing their strategy. So in this stag hunt example, if we're both hunting the stag, so if I'm this agent, this yellow agent on the left, we both choose to hunt the stag, and I individually change my strategy to hunting the rabbit, well, now I get a lower payoff. So I've got a smaller animal. The other agent is much worse off, but I don't care about them. So I've got a worse outcome by changing my schedule. And the same is true for this top agent. So hunting the stag is a Nash equilibrium. And it's pretty good, right? This is kind of the best outcome. In some sense, this is the best outcome for the whole population. But there is another Nash equilibrium, which is we both hunt rabbits. So if we're both hunting rabbits and I change my strategy, where am I? Yeah, if I change my strategy and I try and hunt the stag, I can't hunt the stag by myself. So I fail at getting anything, and the other agent, they get something I don't care about. So I can't improve my outcome by changing my strategy. So again, this is a second Nash equilibrium. So they are different in terms of the total payoff for the whole population, but they are equilibrium, they're kind of stable. So agents, they don't have an incentive to change from this strategy or this schedule we have assigned to them. And that's, it's a difficult problem to solve, but it describes the problem relatively well. Okay, so using the same language, let's look at the virtual power plant problem. So also non-cooperative game. And so for each of our agents, we have more than two, we have however many. They each have an objective, which is to minimize the cost of power. So the price of buying electricity to charge my bank, and also the profit I get from selling electricity. And also I want to minimize how much I don't like the schedule that is being assigned to me. We also have some constraints. The constraints are slightly more complicated than in the stag hunt, where you have just two choices. So in this problem, there's a difference between schedules I don't like and schedules I cannot do. So if I need to drive to work in my electric car at 8 a.m., then it needs to be charged by 8 a.m. That's a hard constraint, not a preference. So our schedule needs to fit your personal routine. We have limits on how much you can charge and discharge, just based on how big are your charging cables and how powerful are your power sockets. We also have constraints on how much power can we fit in the power bank. You can't charge below 0%, can't charge above 100%. And finally, we have some constraints on the power grid. So the power grid has a capacity on how much power it can store. And also, we don't want to dump power into the grid that no one is there to use. So having free power floating around the grid is, I think, a good way to blow up the transformers. So we want to avoid that. So there's two things I want to highlight here. So the cost of power and the grid capacity constraint, these depend on not just my actions, but everyone's actions. So the grid capacity, right, how much power is there left in the grid, it doesn't just depend on how much I'm taking from it, it depends on how much everyone is using. So this depends on the behavior of all the other agents. Similarly, for the power cost, the cost of power depends on the demand for power, which then depends on how much are people buying, how much do people want. So the problem for each agent is coupled. It's connected to the problems for all the other agents through these two parts of the problems, the objective and one of the constraints. So, well, if you're wondering where the generalized bit comes from, it's because they're connected through the constraints. It's kind of a technical aside. So what is our generalized Nash equilibrium here? Well, we can't eyeball it like in the stag hunt. I can't make a nice diagram out of it, unfortunately. But we do have an optimization tool for finding them. We have these things, these equations that were found, I think, first by Parrish and then by Kuhn and Tucker. And I'm not going to write down what they are, but we have some set of equations that says, if you want an optimal set of schedules, a Nash equilibrium, they are the solutions to these equations. So if we solve this set of equations, then we have found a generalized Nash equilibrium. And so this is where we move from the game theory model background into our optimization tools. So unfortunately, if we want to solve these equations in this setup, traditional optimization methods are difficult to apply here. So for a few reasons, first of all, our objective might not have a gradient. So if one of our traditional optimization methods is gradient descent, well, gradient is in the name. We need a gradient in order to use it. We might not have that. So we're in a bit of a difficult spot if we're trying to use gradient descent. Also, our information for the problem, all these constraints, all of the data on electricity price stuff, might be kept in different locations. They are personal to each agent. They might be private, and collecting them might take a lot of time, take a lot of money to get someone to go and do it. It might be violating their privacy by trying to take their electricity prices out of their hands. So this can take a lot of time. So if I want to try and solve this problem on my laptop, I'm the I in this case. If I want to try and solve it on my laptop, I need all the information on my computer to do one of these traditional optimization methods. So a little tricky to do in this case. What we are going to turn to is what's called distributed optimization methods. So instead of having the all-seeing eye in the middle, which is me and my laptop, instead we're keeping the agents as they are, and they are connected to each other in some way. Everyone's not connected to each other, well, everyone's not connected to everyone else, but they're connected to some subset of the agents, so that eventually I can move from agent to agent and get to someone else. So we can resolve the challenges I just talked about. Each agent gets to keep their information private to some extent. They don't need to send it all to me and my laptop. And each of our agents is going to solve smaller problems in parallel rather than me trying to solve the whole thing all at once. And they are going to share some information with their neighboring agents, but it's just the results of these problems, not the full data set. They're not going to try and communicate the whole data set of their electricity price to their neighbors. So when I say neighbors, I'm going to keep talking about neighbors. What that means is we've got this network of agents. Agents are connected by lines, which says, I can talk to someone if I'm connected to them with a line. And anyone I'm connected to with a line, that's my neighbor. Okay. If you're familiar, if you have done any graph theory, it's just the definition of neighbors. Okay. So the problem we want our agents to solve in this distributed optimization setup is agent I wants to find a schedule. I'm going to call that X, or X subscript I is agent I's schedule. I want to find a schedule Xi that minimizes my cost, which is personal to me, cost subscript I, and it depends on the behavior of everyone else. So it depends on everyone else's schedules, which is X1, X2, blah, blah, blah. We're stopping at X10 because this example only has 10 agents, but this goes on for how many agents you have. And not just that, but we want our schedule Xi to satisfy our personal constraints. So that's how much can I charge and discharge in my house? What's my routine like? When do I need to charge? Blah, blah, blah. And then also we have these grid constraints. So based on everyone's schedules, X1 plus or up to X10, we want these to satisfy the constraint on the whole population, like don't blow up the power grid, please. So if we run through kind of a broad picture, what do these distributed optimization methods look like? We've got this, here's this random network of 10 agents. I've just put some lines in here to give everyone some neighbors. And if we put ourselves in the shoes of agent number 5, so agent 5 has 2 neighbors, agent 3, agent 7. So I'm connected to them with a line. And what agent 5 knows is agent 5 knows their cost function, cost subscript 5, and also their personal constraints. And we know our neighbors know their cost functions. I can't get to them, but I know they know them. So what I can do to try and solve this bigger problem that depends on everyone else's behavior is I can communicate to my neighbors, here's what my cost function looks like for a particular schedule or a particular set of schedules. Or maybe some more complicated information like here's the gradient of my cost function at a particular schedule. So I'm not giving them the formulas, but I am giving them the outputs of these functions. And when I do that, I can also get similar information back from my neighbors. So they can say, here's what my cost function looks like for a particular set of schedules. And so each agent is going to do a set of operations on this information. I'll get to that later. But they're going to do some computational work. everyone's going to do it in parallel. And because our network is connected, I'll just get to in a moment, as we do more and more of these computations, eventually, what connected means is that the stuff from agent 1 can trickle down eventually to agent 5. The stuff from the information from agent 10 is going to trickle down to agent number 5, right? The information from everyone, in theory, as we do more and more of these computations, the information from all the agents is going to be available to agent 5 in some sense, enough that I can try and find a solution of this big problem. Okay. Cool. So this isn't a brand new framework of methods. There are some existing methods for distributed optimization. Problem is, some of them don't work on this problem. The theory completely fails for this problem, or they do work on this problem, which is great, and we like those, but they can be a little slow to find solutions. Maybe slower than we would like, or we think we could do it faster. And that is exactly what we are going to do. To try and solve this virtual power plant scheduling problem, we are going to make our own distributed optimization method or algorithm that can work on this problem, and is also ideally going to be a little bit faster than other algorithms for this problem. So before I get into results on what this looks like in practice, so I said before, these agents are going to do some computations on their own. They're going to do them again and again and again. Everyone's going to do them in parallel. So what are these computations I'm talking about? So first, they're going to find a schedule that is suitable, in some sense, for their preferences and also feasible, that works for their constraints. So a schedule that is possible and also is somewhat preferred. So in technical terms, we're solving a quadratic program. So this is kind of the hard step computation-wise. This is going to make your laptop do some work. Then we're also going to do a little bit with the price of power. So this first step doesn't involve the price of power at all. Then we are going to look at our information, our formula for the price of power, and do something like, where should I move that decreases my price of power? And so this sounds a little bit like a gradient, or maybe a gradient descent. It involves some gradients, but it's not exactly a gradient, so it's a linear operator. But without technical details, it's just we want to find lower power prices, basically. So once we've done that, we're going to communicate the results of these problems to our neighbors, not the problems themselves, just the outputs. And then we are going to combine them, just addition, subtraction, multiplication by scalars. So this last step is very, very easy. These first two steps are the computationally intense part. This is going to make your computer work. And then this third step, this is going to, well, depending on how long it takes to communicate, this is going to be the big time intensive part that isn't very computationally difficult. Okay, so we studied this algorithm a little bit, and we found it has some theory behind it that is points to it's going to perform a little bit better than these other algorithms. And then what I'm about to show is that we have some practical results that shows in some settings we do get better performance. We get solutions faster. And so what I'm going to compare our algorithm to is one of these existing methods that does work on the problem is proposed by Yura Malitsky and Matt Tam, which came out this year. So that works on this problem. So I'm going to compare our algorithm to that. Okay, so here's a plot with nothing on it. So on the x-axis, I'm just going to plot what we call iterations. This is like how many times have I done this set of computations, operations with my information. And on the y-axis, I'm going to plot something called residuals. So you can think of this as like how close am I to finding the answer. If you're kind of familiar with how these iterative algorithms work, this is the distance between two variables. Okay, but think of it, smaller is better. Once we hit 0, we have found a solution. The closer we get to 0, hopefully that's a better solution than if we have high residuals. Okay, so here are the results from these two algorithms. So in orange, we have an algorithm by Urmlinski and Matt Tam, and it's doing pretty good. We have a bit of oscillations, but it kind of settles down, and we are decreasing, right? We expect this, we know theoretically this is going to go down to 0. And it's not doing too badly. Then our algorithm in the black, again, we have these oscillations, but we are generally trending downwards faster-ish. So this is promising, right? This is not conclusive proof that ours is, our algorithm is always better all the time. This is one problem with one set of data. So let's do something slightly more rigorous. So let's take a look at what's the quality of the solutions we are getting from these algorithms. So this isn't actually showing how good the solutions are. Or it doesn't show what the solutions look like. So let's visualize the solutions. Again, on the x-axis, I'm going to plot the hours into my time horizon. So this is over 2 days. On the y-axis, I'm going to put how much power each agent is going to charge or discharge in kilowatt hours. So positive means they're charging, negative means they're discharging. And I'm also going to put on here, the red line is the demand for power from everyone else in the power grid. So not the people in our virtual power plant, but the other users who just need power. And so the first strategy we are going to look at, so these little colored bars are how much do my agents charge in each time period. And so the first strategy is like a baseline, is I'm not going to try and optimize anything. I'm just going to charge all the power I need for the day at 3 a.m. when the demand is lowest, when theoretically I would get a lower price. Obviously, this is a bad strategy if you know there are other people also doing this, because as you see, everyone stacks up on top of each other. But this is going to be just our baseline to compare other results to. So the next thing we might think is, I'm not going to communicate to anyone. I'm just going to take all the information I have about my problem. I'm going to do some optimization on that and see if that works as a schedule. And so we get something a little different. Now we see agents are buying when demand is low, and they are selling some electricity when demand is high, and also satisfying their own personal energy usages. So they're buying enough for them to use throughout the day, but then also enough to make a little bit of profit by selling it when demand is high, and by doing this, ideally, lowering their total power bill. Okay, so these were just not even heuristic solutions. These are just good ideas that I came up with that it might be smart for you to do if you weren't doing something sophisticated. But now I can plot the solution that we get out of our algorithm. So the problem with this individual optimization is we're not talking to anyone else. And we know that the price of power is dependent on demand, which depends on the actions of everyone else. So if everyone charges at the same time, that's going to increase demand, increase the price of power. So if we start communicating with other agents, we start learning what the actual price of power is going to be, we are a lot more conservative in our decisions. Because now when we're more accurately seeing what the price of power is, in this individual optimization case, we are underestimating how expensive electricity is. So we are making bigger purchases, we can sell more, and everything's going to be great. But then once we, by putting some communication into our algorithm, we see actually it's more expensive than I thought because everyone else is doing the same thing as me. Let's be a bit more conservative in how much power I'm buying and spread it out a little bit off the peaks of the demand. Okay, so again, this is not a very rigorous comparison of the algorithms. This is one instance of our problem, one set of data. So let's do something marginally more rigorous. And I'm going to run it over 10 problems and average it out and see how these strategies do. So as our baseline, everyone charging what they need at 3 a.m. and calling it quits. We say if we add up everyone's power prices for their whole schedules, this solution would end up being $343 over 2 days. Okay. So this strategy of independent optimization without communicating to anyone, that does actually work in driving down the total power prices. It doesn't capture if everyone is kind of better off. And this is not going to be a Nash equilibrium. So people can still try and screw over someone else to get a better power deal. But it does work in driving the total power prices down by about 2/3. So then if I take a look at what is the solution we get out of that algorithm by Militsky and Tam, then we do quite a bit better again. We're now down to 86% reduction from our baseline case in the median case. And so what does our solution look like? Not too different. It's a little bit of a difference, but they are kind of the same solution quality in terms of the total power price. The difference is if I go all the way back to this plot, we are getting there quite a bit faster, on average. Like if we look at all those 10 instances, we're going to see the same kind of behavior here. So we are finding the same kind of goodness of solution a little bit faster.
Are they related Nash equilibriums?
These two are Nash. Well, these two are close to Nash equilibrium. These two are not. I picked them. This is kind of what you would do if you didn't have any information on anyone else. So these are definitely not going to be Nash equilibrium. Actually, 3 AM, you could, if I change my charge to, if I charge at 2 AM, I get a better price. So it's definitely not Nash equilibrium. Okay, so that's all the results. Summary at the end. So we have a new model for scheduling virtual power plants. We've got a new optimization method that has some advantages over existing optimization methods. In future, we'd like to broaden what are the parameters we're allowed to use in this method. What are the different? Can we include some more possible power prices for slightly weirder ones? Maybe allow agents in this network to drop in and drop out of the network. But there are all of the technical details are up in this archive preprint by myself, Matt, and Joyce. Thank you very much for your attention.